So, having discussed the physico-chemical aspects of iron making in an iron blast furnace, let us talk a little bit about the thermal aspects. Some statements have already been made, and we want to first look at the Raceway region, and in the Raceway region what we see is the combustion which takes place. Carbon as solid combines with oxygen with hot blast, and as a result of which CO is produced. Okay? And and the heat of formation of the blast, at 1200 degree centigrade, I think is about 100, very intense amount of kilojoules per mole. That is the per kg mole. Okay? So, that is the heat of formation of carbon monoxide, and that heat of formation is at 1200 degree centigrade. At higher temperature, it is going to be still higher than this. So, in front of the tuer, really a very intense amount of carbon monoxide environment is there, almost 100%, and because it is surrounded by blues are my all coke particles, it is surrounded by coke. Any carbon dioxide, if it even forms, that is going to be instantaneously converted into carbon monoxide again. So, conversion of carbon dioxide into carbon monoxide will take place, because as I have indicated again and again, that carbon dioxide at this temperature is the most stable phase. Now, the carbon monoxide basically which is generated here, this combustion reaction produces temperature, and then we have a terminology called raft and TFT. The tuer flame temperature, it is the flame temperature because the gas is being injected through the tuers, and this geometry takes place under steady state. Okay? The rate, the combustion rate is the rate at which oxygen is being consumed, and when the oxygen consumption and carbon dioxide enter into the raceway, they match together. In that particular case, what happens, you get a. So, the moment the coke particle comes, tries to enter here, what happens, it gets oxidized into carbon monoxide, and then this sort of a geometry. So, it is a hollow region in front of, and that one can see actually from an outside through the window which modern blast furnaces are equipped with. Okay? The coke enters here, but vanishes momentarily, converts into carbon monoxide. In the process of this combustion, the coke contains, we must understand that is going to be useful, the coke contains sulfur, it contains silica, that is a coke ash, it contains calcium oxide, and these are the major impurities which are present, and that is the coke ash, and that coke ash can be taken up by the gas. So, this white line which I am showing is the carbon monoxide gas which is rising up, and as it rises up, its concentration changes. Tuer flame temperature basically is approximately, as I have indicated, is 1900 to 2000 degree centigrade. That is the temperature that is normally maintained in the blast furnace. This temperature will depend on the composition. Suppose if you enrich the oxygen a little bit, that temperature will go up. If you, for example, use a little bit of moisture here, because of endothermic reaction, that temperature may go down. So, it is a process dependent parameter, but most of the blast furnaces try to maintain it. Modern day blast furnaces, big blast furnaces try to maintain it at tuer flame temperature is about 1900 to 2000. Then the blast furnace operates smoothly. Raft, the raceway adiabatic, this is a flame temperature. This is for the sake of calculation, and this is calculated. There are standard formulae which are available, and these are simplified calculations because it is an adiabatic. So, this temperature calculated on the basis of the formula is available give you much bigger or higher temperature than the TFT. So, one I think expression, if I remember correctly, I think it is 4.6 multiplied by 1.4, the flame temperature is equal to something like 6280 plus 2269 plus maybe 4.4 into 1.4 into T sub B. What are these terms? Because when you do an adiabatic calculation, so this is the heat which is being generated because of the carbon monoxide oxidation. Okay? And this is the sensible heat of the coke, because the coke is entering here not at room temperature, but the coke enters here at a predetermined temperature of 1800 or 1900 degrees centigrade. So, that is the kind of temperature on the basis of which the sensible heat is calculated, and I think these are all per unit mass basis, and these coefficients here are basically the terminal is a measure of the specific heat as well as the density of the gases. Now, this is the flame temperature and this is the blast temperature. At what temperature the heat is coming into the, of course, there are losses to the wall, there may be other injectants which may be consuming, those are not taken into account. So, no loss is there, and that is why the temperature that is calculated becomes an adiabatic, and the resultant flame temperature is called adiabatic flame temperature. It essentially tells us that as you increase the blast temperature, this is the most important information that we can get from this expression, as you increase the blast temperature, the flame temperature also increases. Now, the gas rises up, and what happens is that during the rise, this hot gas is progressively giving heat to the surroundings, which are coke particle and ore particle, and it cools down in the process of rising, and the gas, while the solid it moves very slowly, the gas rises extremely faster. Okay? So, within few minutes, the gas which is generated here, because of the large pressure difference, even though there may be a large resistance in the path of the gas in terms of the solid particles present, then what happens is that we have very quick ascending velocity of the gas itself, but the gas in the process gives rise to, yields its heat to the solid, and the solid progressively heats up, and the temperature of the solid also keeps on increasing as it descends. Now, we must understand that I have listed during my last lecture that the gas carbon monoxide concentration is about 20%, that is in the off gas, that is the gas which exit gas from the blast furnace itself. But if a blast furnace is operated under equilibrium condition, and what is here? Here it is Fe2O3, that is what is the layer which you have charged into the furnace. So, if the gas moving out is going through several stages of equilibrium, and finally it lifts the furnace with equilibrium, then the concentration of carbon monoxide could have been just 1%, because I made that statement that look 1% carbon monoxide atmosphere will even also reduce Fe2O3. So, virtually if the blast furnace is operated at equilibrium, that there are equilibrium stages established at various stages, then the final equilibrium will dictate that the carbon monoxide concentration is close to equilibrium. But that carbon monoxide concentration is not close to equilibrium, it is significantly higher. Essentially, it tells us that the potential of the gas has not been fully utilized, and the blast furnace is operated away from the equilibrium. Indeed, CO measure in the blast furnace top gas is a measure of its efficiency. Smaller is the CO concentration in the blast furnace. Okay? Therefore, we will see smaller is the concentration of CO in the exit gases, we will conclude that better is the efficiency of the blast furnace itself, but it is sufficient for us to remember that the blast furnace operates away from the equilibrium and there is significant amount of CO. And you can imagine, for example, if the blast furnace is very small, what would happen to the concentration of CO? Everything else remaining same, I would say that the concentration of CO is going to be higher. The temperature of the gas, exit gas, which is normally 300 degrees centigrade, okay, that is going to be much higher if the blast furnace height is small. So, therefore, all the modern blast furnaces are very tall structures, but again there is a limitation to it. We cannot build a very tall structure because we are looking for a good strength of the material. If you build too tall a structure, in that case all the solid particles may crumble into pieces, and as a result of which the efficiency of iron production in the blast furnace, instead of getting improved performance, we are going to get an impaired performance of the blast furnace itself. So, therefore, there are limitations, material property limitations based on which beyond a certain level blast furnace cannot be extended. Similarly, blast furnace cannot be extended much in this direction also, because you will require an enormously large blowers and compressors in order to push the gas right to the up to this particular level, because we want the gas to penetrate much deeper, so that we do not have a huge this region which you call as a dead man's zone or inactive coke region, and that is basically there because the gas has not been able to penetrate. Okay? If the gas is able to penetrate right up to the center, in that case this may not exit. We of course do not want gas to penetrate here, because we do not want that all coke should get burnt away in this particular region, then the bed porosity is going to be lost. So, dead coke mass. Dead coke mass essentially means this coke mass does not move, they are not subjected to oxidation because the gas do not reach there, they do not take part in any reactions. So, that is basically referred to as the dead coke mass. Now, so if you have a tall structure, if you have a short structure, this gas temperature will also be greater than 300 degree centigrade. So, the thermal economics of the blast furnace will therefore, the chemical efficiency of blast furnace is dictated by the top gas composition, the thermal efficiency of the blast furnace is dictated mostly by the temperature of the top gases. Now, if you, as the reduction reaction takes place, we must understand that there are going to be lot of the iron ore that we charge that have lot of impurities, and I have already mentioned that we have impurities like silica, alumina. These are my major impurities in the iron ore, and titanium dioxide. Coke impurities I have given. Limestone also, we can say that limestone contains silica, and we have iron ore contains this, and coke, as we have seen, sulfur. Iron ore also contains some phosphorus, okay? Sulfur, phosphorus, then calcium oxide, silica, these are the impurity presents. And of course, the air can contain nitrogen, that is also an impurity, and that nitrogen is going to manifests within in the top gas itself, it remains unchanged. So, the gas from here, from 1900 in a modern blast furnace will go down to 300 degree centigrade at the top, and it essentially implies that the gas yields its heat to the solid particle, and then so the gas temperature progressively decreases. So, I would say, as I have indicated, in the lower stack region I could have something like 900 or 1000 degree centigrade, upper stack region something like 500 degree centigrade, okay? Then much lower below here about 1200 1300 degree centigrade, and then finally here about 1450 to 1550 degree centigrade. That is how the temperature, quite a bit of variation of temperature in the system. We must understand the gas has a predominant tendency to advect the heat in the upward direction. So, therefore, what happens is this is, even though this is 1900 degree centigrade, we do not see, this could be about 1300 to 1500 degree centigrade, okay, in this part, and it is about 1900 degree centigrade, it could be about 1800 1700 something here, okay. The temperature here, the radiation effects are in all directions, okay, but the convection takes the gas, and therefore, we see that this temperature I have written 1450 to 1550, I essentially mean that this slag, which is the white color thing, is at a higher temperature because it is close to the flame here, okay, and this is at a relatively lower temperature. The metal to slag temperature are going to be somewhat different, 50 degree difference, typically slag having 50 degree centigrade more than the metal because of its proximity to the tuer. So, having said that there is an intense carbon monoxide atmosphere in the furnace, and we will draw the carbon monoxide profile. So, you can imagine from 100% carbon monoxide at this particular level, we have in the gas, in the carbon monoxide, if you consider on, forget about the nitrogen, okay, then you can see 24, 45. So, this is about, in the carbonaceous mixture we have about 45% CO2, just the carbonaceous mixture part. So, in 45 it is 20. So, in 100 it is roughly about approximately about 45% CO. So, there is a significant change in carbon monoxide concentration, okay, and there is a significant change in temperature also. So, therefore, it is important for us to see that how these impurity elements are going to be behaving. So, we understood that iron ore will undergo reduction, and then iron, liquid iron is going to be produced, but what will happen to silica, what will happen to Al2O3, what will happen to titanium oxide, that reals. Now, oxides like calcium oxides and magnesium oxides are very stable. Okay? This temperature of 1900 degree centigrade, which is the maximum temperature, and even 100% CO are not enough to reduce this. So, they stay as it is. Same is true with alumina. It is a very stable oxide. Blast furnace, in blast furnace alumina will never get reduced. Reduction of alumina, as I have mentioned, 2200 degree centigrade is needed. And then we have silicon. This undergoes partial reduction. Titanium oxide undergoes partial reduction, and silicon dioxide, sulfur, okay, this is partially partition. Phosphorus again is completely partition. Since we have a progressively higher temperature, and as I have said that once Fe forms, solid Fe forms after reduction, and then liquefaction of iron takes place, and that is what I have shown here, that the iron, liquid iron will trickle through the coke bed, this dead zone, and as a result of which what happens, it is just like sugar dissolving in water. So, when water will flow past a sugar block, sugar will get dissolved into water. So, when the liquid iron is going to flow, that liquid iron has a great solubility for carbon. So, therefore, it is going to pick up from this bed of carbon or coke which is there in the dead mass of the coke. So, the iron will contain, liquid iron will contain obviously carbon, and the source of carbon is because the blast furnace is packed with carbon, and that carbon has great solubility, and that solubility is enormous at still iron making temperature. So, we can get carbon somewhere around 4 to 5 weight percentage by weight percent. Now, about phosphorus, for example, if you look at Ellingham diagram, the phosphorus pentoxide line and iron oxide FeFeO line are absolutely close, which essentially means that if an environment and temperature can reduce FeO, that will reduce phosphorus pentoxide for within the furnace. So, therefore, we can say all those elements which are reduced in the blast furnace are going to go into the metal phase. All those elements which are going to stay as of their oxides, they will remain in the slack phase. So, there will be a combination. So, CaO MgO will remain as it is, Al2O3 will remain as it is, but silica and titanium dioxide are certain, they are the two constituents which depending on the temperature as well as the carbon monoxide concentration where they are subjected to, they can undergo reduction, some reduction, I will write the reactions, it will be clear to you, some reductions and some remain as it is. Those portion of silica which will get reduced will join the metal. Now, reduction of silica to silicon is an endothermic reaction. So, that reaction will take place basically at the lower part of the furnace, where reduction of silica is not possible here, it is possible here because we require, it is a oxygen silicon bond is extremely heavy, strong. So, therefore, we can say that silica to silicon reduction will take place in the lower part of the furnace, where we have more intense carbon monoxide, more higher temperature. But depending on the temperature, therefore, it is understood that if the blast furnace raceway temperature is increased beyond 2200 degree centigrade, okay, or 1900 degree centigrade, we can see that there is more reduction of silica taking place, and as a result of which the hot metal silicon content can increase. Now, the hot metal silicon has a great bearing on the next step of steel making, because that is the source of heat. Carbon and silicon are the source of heat which makes the steel making process autogenous, particularly the basic oxygen steel making process, which we will study in this particular course. So, the operating condition of the furnace, what is, how much of silica is coming into the system, what is mostly the operating temperature, and most importantly what is also the basicity. That is, because if you have more basic slag, the slag will contain all of these oxides. So, the slag, for example, if you look at here, the slag will contain, as I said, CaO, MgO for sure, Al2O3, they do not undergo reduction, and some of SiO2 because Si and some titanium dioxide also, because titanium dioxide and silicon dioxide or silica are those two oxides in blast furnaces which can partition, because the condition is in the borderline. Okay? They can partition between the slag and the metal. If the portion of silica that gets reduced comes to the metal, and also same is true with sulfur. Some sulfur can go to the slag and some sulfur can remain in the metal. So, that virtually dictates the slag and the metal composition in a blast furnace. Their proportion, what is the percentage of CO, what is the percentage of silicon, these are all going to be dependent on the characteristics of the feed material fed into the blast furnace as well as the operating conditions, as it will be clear to you in a short while. Now, if you look at the blast furnace, people have dissected the blast furnace in a pilot scale blast furnaces, and the blast furnaces are shown to be characterized into different regions, as I have tried to depict a picture here. One such region is, this is called the granular region, where mostly solid particles are there. The temperature is, some reduction may have taken place, coke, lime and ore, they are all intact. So, granular particles, the solid particles maintaining their rigid shape, that is the region. And then below the granular zone comes the cohesive zone, okay, where partial melting has taken place. You remember that when I was talking about sintering and pelletization, I said that the slag bonding is that which around 1100 degrees centigrade, which gives strength to the pellets as well as the sinter, and the slag bond form because silica is present, because CO is present, because FeO is present, and same thing is going to happen here also. Predominantly FeO, this is the first liquid constituents that appear, which is called as a fhyolite, ferrosilicate. And this liquid tries to bond the solid particles, and that is what we see in a cohesive zone, where we can have some lumps. Okay? Coke is of course going to be lumpy always, because coke does not melt. Okay? Coke remains either when it oxidizes in the raceway, but elsewhere in the furnace coke is either available as dissolved carbon in the metal, or coke is available as a lumpy coke within the blast furnace itself. So, as the temperature goes down, maybe about 1000 to 1100 degrees centigrade, that is the temperature where you can see incipient fusion can take place, and as a result of which, okay, and you remember that our temperature is increasing as we are travelling down. So, below the granular zone you will find a cohesive zone, and that cohesive zone will contain basically FeO, a combination of iron oxide and silica. And now with further more temperature, as it descends further, then what happens, proportion of this is increased, and also what happens is now the lime becomes active. Okay? Lime started to become soft, and the lime has it's a strong basic oxide, and it has a great affinity towards FeO. Then what happens is the lime tries to replace FeO, and then the moment lime is able to replace FeO, that FeO will undergo instantaneous reduction, because the temperature is extremely high. So, as a result of which, below the cohesive zone, okay, so I can say granular zone, and then we have a cohesive zone. Where the first liquid starts to appear, okay. And below the cohesive zone, what happens is we have a slag phase, liquid slag containing calcium oxide. This is below the cohesive zone, calcium oxide, silica, maybe alumina, and below the cohesive zone mostly the iron oxide does not exist. Okay? All has been converted, because by 900,000 degrees centigrade, reduction of iron ore in an atmosphere containing 100% CO2 CO is almost complete. So, the slag below the cohesive zone will contain, with progressive replacement of FeO from the silica matrix. So, it will contain this, as well as, and these are as the what you call the oxides are being taken, this coke is burning, ash is being liberated. So, the silica is taken and then the basicity of the slag is progressively changing as it is descending down because of the various reactions taking place, that progressive replacement of FeO by CaO and continuous dissolution of silica and alumina into the slag dynamically changes the basicity of the slag, which I have defined. The simple definition, or this is called the V ratio. There are other definition of basicity also, which we may see later on when we do the steel making, but it is sufficient for us, and these are percentage wet percentage CO versus wet percentage CO. So, this changes dynamically. Now, we must understand that if the slag volume is more, or if we require a higher basicity for some reason, we will see what is that reason itself. In that case, we may have to operate at a very high temperature, because CaO does not get soften, or it dissolves in calcium silicate. Further progressive dissolution of CaO in a CaO SiO2 system will demand more temperature, and as a result of which what happens is that we may land up, for example, getting more amount of silicon, because I have said that higher is the temperature, more, and temperature higher is the temperature means in the lower part of the furnace you are going to get more reduction of silica, and which is going to land up in the hot metal phase itself. So, the slag becomes liquid, then your solid iron, which is still there, that solid iron, it absorbs, it gets carburized and it forms FeC. So, these are all happening beyond the granular zone. Iron gets carburized, and as a result of which what happens, the melting point of iron decreases. We all know that if you look at the iron carbon phase diagram, then we can find that with progressive dissolution of carbon, the melting point of iron changes, and as a result of which at certain point below the cohesive zone we get liquid iron. So, liquid iron is formed, and the slag, and the liquid iron forms as well as the slag forms here, and as they go down, their composition continuously changes as they accumulate here. And even when they accumulate here, the slag being lighter, oxides are lighter, there are reactions taking place, and the slag and the metal trying to arrive at equilibrium, chemical equilibrium with respect to each other, there also the composition is taking place. So, the slag formation reactions, many slag reduction reactions take place, limestone calcination reaction takes place, okay. Then we have carburization reactions takes place, slag formation takes place, and then the slag metal reaction takes place. I am not trying to say that slag metal reaction will not take place here. These lines show the white arrow is the slag and red arrow is the metal. So, as they trickle down through the bed of core, they come in contact with each other and they can exchange heat and mass. So, there is a continuous process along the height from the top to the bottom, chemical reactions one after another will be taking place, and that is going to ultimately determine that what is the slag composition and what is the metal composition. But constituent wise, okay, this I cannot say that if I write here for 1%, 1 weight percent, there is nothing like a sacrosanct hot metal composition, because as I said, it depends on the raw material that you are charging into the furnace, it depends on the practice. So, practices are different in Japanese steel plant than in Indian steel plant. Raw materials, even in India, for example, Tata Steel may be getting raw materials from some places, Jindal may be getting raw materials from some other places. But the real engineering challenge is that having gotten diverse types of raw material in blast furnace, how can you engineer the process? So, day in and day out you can get a consistent metal quality. Okay? I have a 5% plus minus tolerance, and within that, no matter what is the characteristics of my coke, what is the characteristics of my iron ore, what is the characteristics of sinter, I will ensure that I can engineer the blast furnace operation at just its temperature, pressure, oxygen or air flow rate, etc., in such a way that the hot metal is produced with a consistent quality, and that is the real challenge on a daily basis as far as blast furnace operation is concerned. So, granular zone is one, cohesive zone is another. This is the raceway or the two-air zone, this is the 3. Then we have the dead man coke mass, which is zone 4 and this is the blast furnace. Internally HEA R3H. So, you can get now a good picture, internal picture if you close your eyes, and then you can visualize that how really the inside of a blast furnace looks like. So, in the top part we see the granular particle, and then we see that the proportion of the granular particle decreasing and decreasing and liquid started to appear, and then what happens is ultimately if you go down we have just solid coke particle and liquid flowing all around it, and then at the bottom of the furnace we have two different layers of liquid, the slag and the metal with a common interfacial contact. That is what really one can see inside the furnace. And this people have seen, people have frozen blast furnace, not industrial size blast furnace, but pilot scale blast furnaces, and then they have sectioned the blast furnace vertically. This work happened I think long time back in Japan, and that is how people have developed a good understanding, and this is quite logical and it fits our theoretical understanding very well, and which has also been, as I have just now mentioned, confirmed by dissecting iron blast furnaces itself. So, given this picture, now the blast furnace reactions can be tabulated, that what are the various reactions zone wise. So, in the granular zone, or I would say upper stack, STSCK. So, we have predominantly Fe2O3 solid. There are many reactions that are simultaneously occurring, but all those reactions need not be tabulated here. Okay? So, for example, sometimes what happens, because if it is also possible that if in this part if some FeO has locally generated, then that FeO in the upper part is going to be reoxidized into FeO, Fe2O3 or Fe3O4. So, all those kinds of nitty-gritties may not be taken, but ideally speaking, if we travel from top to bottom, we can tabulate reaction, region wise, that what are the characteristic equations, chemical reactions which take place in the blast furnace. Okay? And this gives us Fe3O4, and then we take solid, and then you get and then we get something around Fe3O4 solid plus CO gas, and then we get FeO plus solid plus CO2. That is, these are the predominant reactions. These reactions may be completed in the upper part, upper stack region. These reactions may not be completed in the upper reaction part. We go to the lower stack, and there temperature is about, we are talking about lower stacks somewhere around here, not yet into the cohesive zone. Okay? And here what happens is we can get something like calcium carbonate calcination, what is calcium oxide. What is the heat effect of these reactions? Negligible heat effects, but this is a strongly endothermic chemical reaction. Okay? And here in the lower stack region we can have gasification reaction started to occur, CO2 plus C giving rise to, and then we have FeO solid plus CO gas is equal to this does not mean, I do not mean that this reaction is impossible in the blast furnace. For example, if a coke particle comes in contact, and at that interface between the ore and the coke particle, there may be this reaction also taking place, but the significant reactions are what I am listing, and that is what is shown in this particular case. You must understand here that if you combine these reactions together, okay, this carbon dioxide and this carbon dioxide will cancel out, this carbon monoxide and this carbon monoxide will leave some carbon monoxide here, and then we can say this reaction plus this reaction becomes equivalent to this particular reaction. So, this is what I am trying to say. These two reactions together is taking to be equal to this particular reactions. So, if these reactions are taking place simultaneously, one can say that I can represent this reaction by this, but fundamentally speaking they are different, because these are gas solid reactions and these are solid solid reactions. This is carbon is solid, FeO is solid, but stoichiometrically, reaction wise, chemical reaction wise, this plus this is equal to this. Now, this reaction, therefore, we can say this is called the direct reduction reaction, and this direct reduction reaction is a highly endothermic reaction. On the other hand, this is an endothermic reaction and this is an exothermic reaction. That of course, endothermicity is stronger than exothermicity, and that is why the net combination of this becomes an endothermic reaction. Now, therefore, we can make that statement: direct reduction reaction in an iron blast furnace is equivalent to an indirect reduction reaction, because it is indirect CO, plus the Boudouard reaction or the gasification reaction. Gasification reaction combined with the indirect reduction reaction becomes equal to the direct reduction reaction. And we can immediately understand that the temperature will have a great role, because the overall effect is endothermic, and also that there is a change, net change in the volume, from the left to the right, that you have 1 mole of carbon dioxide and 2 moles of carbon monoxide. So, therefore, the pressure and temperature will have an increasing role, influence on the extent of the direct reduction reaction within the blast furnace itself. So, therefore, I would say make that statement categorically by by maneuvering the pressure, because blast furnace has a enormous range of temperature. So, by maneuvering principally the pressure within the furnace, it is possible to control the extent of the gasification reaction, or in turn the direct. How much direct reduction will take place, how much indirect reduction will take place, that relative proportion can be maneuvered by controlling the pressure within the furnace itself, and we will talk about that when we talk about the construction, the developments in modern blast furnaces during the last 50 years or so in a later lecture. So, lower stack, and then we have Fe has formed, and then of course we can say that here it is also possible that ferrous silicate has also formed, FeO plus SiO2, and that is a liquid phase. The iron thus produced is a porous iron, okay, because lot of oxygen has left the mass, and as a result of which what happens is the iron ore lump or the sinters, etc., they have developed porosity, which of course you cannot see. You have to look at it under microscope in order to identify those porosity. So, because these are pores and that the environment is full of coke, so therefore the coke particles tends to get impregnated inside. So, therefore, they are not pure iron per se, they contain a good amount of carbon, okay, within the matrix of iron. Now, as this particle they descend further, then what happens is the intensely reducing environment region is attained. In this region, as you can see, I have drawn that here the temperature is much higher, 1500 degrees, 1600 degrees centigrade. Here we have at that temperature it is 100% CO. So, now the liquid and the solid, whatever is there, in the descending charges, lime is entering into that hot region, iron as solid containing carbon is entering into that region, FeO SiO2 in the liquid state is entering that particular region, okay, as the charge starts to descend down in the furnace, and there are compositional changes that take place, and therefore, we can say that this is the moment FeO SiO2 forms, and this FeO SiO2 plus carbon which is there, and then we have calcium oxide which is also there as a result of limestone cancellation, can give rise to calcium oxide SiO2 plus CO. because no FeO is available, and that no FeO is stable. So, CaO is going to replace, because it is a stronger basic oxides than FeO. It wants silica, silica is a strong acidic oxide. So, there is a huge amount of attraction between the two, and as a result of which iron oxide, which is a weak basic oxides, gets replaced, and we form CaOSiO2, and that the surrounding is rich in carbon, the FeO thus liberated from its phyllite gets reduced, and as a result of which Fe forms. Further down we can have sulfides. For example, we have silicon dioxide. As I said that the charge is descending, we are not going to look at what happens to they do not undergo reduction reactions. So, basically these remain as it is, as I have indicated, and then they form the slag. They only replace certain oxides. For example, this is also possible. I could have written here MgO, that is also a possible reaction, and that will happen if MgO comes in contact. We must understand that the reactants must come, these are all heterogeneous reactions, they must come at a location, meet at a location, and then only the reaction can take place. So, silicon, this can produce, for example, carbon is there, and then we can produce silicon suboxide, which is a gaseous phase, and then we can produce carbon monoxide gas. Suboxide is a, then you can say silicon suboxide, then sulfur is there, and that gives rise to silicon plus sulfide plus carbon. And these are happening below the lower stack. So, I am going down. Okay. So, up lower stack as you enter, limestone calcination, solution loss reaction, reduction of iron FeO, and then formation as you go further down, little down, then you have phyllite formation. Go further down, you have replacement of lime from the slag, and as a result in this, when it forms this and this becomes liquid, into which Al2O3 can also dissolve, because these are all acidic, these are all oxides. So, Al2O3 finds a friendly environment, so it tends to dissolve into the slag itself. The moment the composition, so you must understand the composition of the slag is changing, its temperature is changing, so that its physical characteristics is also changing. The basicity is changing, okay? The chemical composition is changing, the viscosity is changing, the density is changing, all the parameters of the slag is changing, and they will determine the kinetics of the reaction, because kinetics, as you know, mass transfer coefficient, for example, it is a function not only of velocity that I have indicated, but it is a function of thermophysical properties as well. So, progressively the CaO-SiO2 mixture will get some Al2O3. The unreduced titanium oxide can also get into it. What happens to silicon dioxide? For example, titanium suboxide will not form, but titanium oxide can go get reduced, and that titanium can land up in the metal phase itself. So, this silicon sub can again, it is an unstable phase, and this what happens is decomposes this third bracket basically essentially indicates that they dissolve into the metal. So, silicon gets transferred into the metal, sulfur gets transferred into the metal. In the iron ore, we also have an important constituents, which is iron and manganese in the periodic table are very close, they are like brothers. So, what happens to iron also more or less happens to MnO. So, the blast furnace slag virtually will not contain any FeO or MnO. So, FeO and MnO which are present, manganese oxide which are present in the ore, okay, these will undergo complete reduction, because again I said phosphorus line, iron oxide line, Mn line, they are very close. So, high carbon potential and then high temperature will reduce. So, therefore, whatever MnO is there even if it gets into the slag, ultimately what happens is it can, when it comes in contact with the metal, then Mn gets transferred into this reaction. I would say, maybe this I would say that lower stack and below the lower stack, I would say these reactions could be taken to be in the Bosch part of the furnace. Bosch is this particular part, the vertical, bell shaped part, and a little bit of this. So that is what basically, it is not above the 2 of course, and then below the cohesive zone, that is what is. So lower stack, okay, upper stack, and then Bosch region, these are the reactions. And in the Bosch, we must remember that we have very high concentration of carbon monoxide, almost PCO is equal to 1 or 100% CO, and the temperature is also varying between 1500 and 1900 degrees centigrade. So it is the Bosch region that the slag metal composition gets dramatically adjusted because of various kinds of chemical reactions which can take place, and as a result of which we produce a hot metal, as I have indicated here. I think I have erased it. So that will contain mostly, the hot metal will contain iron, hot metal will contain carbon, hot metal will contain silicon, hot metal will contain some sulfur, and some sulfur because we have calcium oxides also here. So it is also possible that calcium oxide which is present can react with sulfur. Sulfur, calcium has a relatively more affinity towards oxygen than to sulfur, but sulfur has a very good affinity towards calcium. So if the sulfur concentration is high, then that sulfur concentration can replace the oxygen and form, particularly in a reducing environment, okay, where carbon has great efficiency to affinity towards form calcium sulfide, which can go into the slag and then we can form carbon monoxide. This is again a reaction which will take place in the Bosch part. I can go on writing reactions one after another, but I think that is not the objective. But I am trying to make that point out, that how does the slag and the metal composition evolves below the lower stack region as the charge passes through the Bosch, and that is the point I am trying to make, and to show that, well, the slag forms because of progressive replacement of FeO by CaO, into which Al2O3 dissolves, and the slag thus contains CaO, Al2O3 and SiO2 predominantly, some titanium oxide which will not be reduced, because titanium oxide, I have said, they will partition between slag and metal. Okay, they are at very high temperature, very intense carbon monoxide concentration. Only carbon monoxide can reduce titanium dioxide. So titanium, they are partially reducible oxides in blast furnace environment, titanium oxide as well as silicon dioxide. And then I have shown that how does the sulfur can get into the slag, how does the sulfur can get into the metal, how does silicon reduction can take place, and silicon suboxide can form, and then from there, we can have the reduction reaction, another reaction which could be carbon plus SiO2, this is equal to carbon monoxide plus Si. That's now if you write this equation, so I will write that carbon is in the solids phase, okay, or carbon could be in the dissolved phase also, same many similar reactions. If I write at this particular interface, I will say that here carbon is there, as I said, the molten metal is rich with carbon, the slag contains silica, so some silica from the slag can get reduced. This is possible in the slag metal interface. This is also possible here also, as the slag trickles down and comes in contact. So I can say that this reaction is possible in the Bosch, and this reaction is also possible in the hearth. The moment I write something with the first bracket, you must remember this is in the oxide phase, and when I write something with the third bracket, it essentially implies that it is in the metal phase. Okay. So now sulfur has gone to the metal, now calcium oxide is there sitting. So if you analyze now, just 2 more minutes and then we will wind up. Okay. So now we have reached, so we have slag and metal. So, we have calcium oxide here, Al2O3 here, and predominant silica is here. Some titanium dioxide may be there, and we may also have some calcium sulphide which is present here. Similarly, we have iron here, carbon here, silicon here, manganese here, sulfur here, phosphorus here. All the phosphorus present in the charge has manifested in the metal itself. Phosphorus cannot go there. I have said it again and again. The lines are very close in the Lingam diagram. This is a slag metal interface. So, it is if you look at it, that sulfur is present in the slag as well as in the metal itself. So, suppose if by chance an FeO which was not exposed to the harsh environment and somehow it had short circuited and found its place in the slag, it is not going to be stable, because the slag metal is going to be in contact for couple of hours in the blast furnace itself. So, as the slag will come in contact, there is a good possibility that if you will come in contact with the dissolved carbon, and immediately what happens, the slag metal reaction, this will take place, and same will happen. So, this is dissolved carbon plus FeO is equal to carbon monoxide, second bracket is gas, and then we have Fe and the slag metal. So, if it is true, this is true, then it is equally true for MnO. So, if MnO is there somehow in the slag phase, that MnO is going to react with dissolved carbon, and as a result of which C plus MnO is equal to CO plus Mn reaction will facilitate. So, therefore, we will say that the blast furnace slag will never contain any iron oxide or never contain any magnesium oxide. Never contain means it is less than 0.1% or something like that, okay? Because the blast furnace environment is highly reducing. If you do the PO2 calculation, then you will find out the oxygen partial pressure in blast furnace is of the order of 10 raised to the power minus 19. No free oxygen can exist in the blast furnace operation. So, we have only one more thing to discuss, that now what is the slag metal reaction. One important thing here is that silicon is the most important, as I said, that if you try to make a high basicity slag, you have to, or if the slag volume is high, you have to have very high temperature in the raceway. If you have very high raceway temperature, one has to write thermal effects of this equation also. This reaction is highly endothermic reaction. So, if you have a very high hearth temperature or Bosch temperature, in that case what happens, predominantly this reduction reaction will be facilitated in the forward direction, and as a result of which the material will be produced with having high silicon content pig iron. So, therefore, the hearth temperature, the Bosch temperature will tell you that how much of silicon is coming into the metal itself. Similarly, if you want to have good basicity, for example, good lime basicity here, you have to jack up the temperature, and then also the silicon content is going to be increased. Now, good basicity is going to be necessary to capture sulfur. Sulfur, as I said, it has good affinity towards calcium oxide. So, because there is a reducing environment already present in the furnace, so sulfur is trying to, carbon is trying to get to this oxygen, sulfur is trying to get, and we have to now create a condition in the blast furnace such that more and more sulfur is eliminated in the through the slag metal contact or in the blast furnace hearth itself, because we will study that in the reaction next class, that elimination of sulfur requires a reducing environment. It warrants the presence of carbon, it warrants no oxygen in the system, and therefore, blast furnace is an ideal site for elimination of sulfur itself. So, therefore, we have to now what we study, that desulfurization in the blast furnace is a very important process, and we will discuss that how the slag, how can we maximize the transfer of slag from the metal to the slag phase within the blast furnace itself, so that we do not face much problem in the downstream process of steel making.